Professor Maya, I think it is time now. So, shall we start?
Sure.
So, participants, ladies and gentlemen, I have the honor and privilege to introduce one of the distinguished speakers this evening, Professor Maya Martseva. She is a professor of mathematics at University of Florida. She obtained her PhD at Purdue University in 1998. After that, she was a postdoc at the Institute for Mathematics and its Applications, University of Minnesota, Arizona State University, and an NSF Advanced Fellow at Cornell University in 2002 to 2003. Since 2003, she has been an assistant professor, associate, and full professor at the Department of Mathematics, University of Florida. Maya Martseva has published around 130 articles. She has also published 3 books, namely Gender Structured Population Modeling in the year 2005 by Siam, an Introduction to Mathematical Epidemiology in 2015, published by Springer. And the third one is Age Structured Population Modeling in the year 2020, again by Springer. Her research has been supported by National Science Foundation. During 2016 to 18, she was a managing editor of Journal of Biological Systems. Currently, she serves as one of the editorial board members of Journal of Biological System, Journal of Biological Dynamics, and Journal of Difference Equations with Applications. With these words, I welcome Professor Martseva and request you, madam, to go ahead and deliver your lecture. The floor is yours, ma'am.
Okay, thank you, Jamal. Good evening, everyone. Thank you for joining me. I know it is kind of late for you. It is kind of early for me, but it all works. Thank you for the invitation to participate in your faculty development program. So I have participated one other time in faculty development program, but then the topic was COVID. And now the topic seemed open, so I decided to talk about something that we have been working on in the last 3 or so years. And this is modeling HIV and the opioid epidemics jointly. And in the last 5 or 10 years, I have been working with the so-called nested multiscale models. These were first proposed in 2002 by Gilchrist and Sasaki, and give a way to model multiscale processes and are particularly adapted for immunoepidemiological modeling. So in this specific model of HIV and opioid epidemics, for the first time, I include also network structure. So it is the end model is a very complex model. I will, of course, show it to you. And without further ado, let me start with the talk. And the slides are not moving. So I'll stop sharing for a second and start sharing again. Still not moving. Technology is a great thing until it stops working, but now it's working again. I will start with a little bit of introduction, introducing, of course, HIV does not need an introduction, but introducing shortly HIV and the opioid epidemic, as well as what network is. And then I will talk about a non-network opioid HIV model. And then I will introduce a network opioid HIV model. And then I will list what basic theoretical results we have been able to obtain for the network opioid HIV model. And then I will, in order to do simulations, you probably know very well that one needs parameters for the models. And I will talk in point 4 about how we parameterized the non-network opioid HIV model. And then using the parameters that we obtained from fitting, we compute elasticities of some important quantities. So I will share this in point 5, elasticity results. And then I will make a summary of the results I have covered. So in the last 10 or 15 years, the use and abuse of opioids in general and heroin in particular has increased immensely all over the world. And the death rate of opioids has been rising. It certainly has been the case in the United States and also China, possibly in India. And you can see here on the right, the national drug overdose deaths involving any opioid in the United States, starting in year 1999 to year 2017. And you can see that these are the blue bars that gives the deaths of any opioid. And you can see that in 1999, there were 8,000 deaths in the United States, but in 2017, there were more than 47,000 deaths. So the opioid epidemic has become a health crisis in the United States and other countries, as I said, China. And heroin accounts for about 1/3 of the drug overdose deaths. On the other hand, as I said, HIV needs no introduction. The United States, we use data for the United States, so this is what I will cite. There are 1.2 million people in the United States who are living with HIV. And you can see the number of people living on HIV on the left on this graph. These are the red dots connected with lines. And you can see that this on the right-hand side gives the number of people living with HIV. In 2008, they were 1.2 million people. This is cited in thousands. So 1,200 is actually 1.2 million. Death rate from AIDS has been declining. You can see the death rate here also pictured. This one is in blue. And you can see that the death rate was rising until about 1995 when the highly antiretroviral therapy was introduced. And after that, the death rate has been falling. And the incidence of HIV, which is not pictured here, is also declining. So opioid use increases the chance of getting HIV. The HIV and opioid epidemics are intertwined. Injecting drug users, which is abbreviated as IDU, may share a needle with an HIV-infected person. So here this figure shows that HIV and drugs are kind of intertwined or joined with each other. 1 in 10 individuals who get HIV is an injective drug user. Drug use lowers inhibitions and makes people prone to behaviors that may lead to HIV infection. HIV-infected individuals who use drugs have poorer health status altogether. And co-infection of opioid use and HIV leads faster to death. And as I said, the model that I will introduce will be a network model. So what is a network? First of all, where does a network fit here? The transmission of HIV creates something called the complex networks. We are modeling particularly the sexual transmission of HIV, and not so much the injecting drug users who actually overlay a different network on the sexual transmission of HIV. A network is a bunch of nodes, which here are represented by these dots. So the red dots represent HIV-infected people, and the blue dots represent HIV-uninfected people. And you can see that the dots are not equally large. Some are larger than others. How big a dot is depends on how many connections this dot has with another dot. So each dot represents an infected or non-infected individual. So the bigger the dot, the more connections the individual has with other individuals in the network. So the number of connections is called the degree of the dot. Actually, as a network part, the dot is called a node. So these are also called nodes. And the links between the nodes, also called edges, gives the number of links, gives the degree of each node. So the typical networks that are useful for modeling social behaviors, such as sexual contacts that lead to HIV, are called scale-free networks. And the scale-free networks are characterized that a few nodes have many connections, and you can see here on this picture there are only 4 or 5 really big nodes, and then there are about 10 medium-sized or less medium-sized nodes, and all the rest of the nodes, which are very many, are very small nodes. So a few nodes have many connections, but most nodes have few connections. And the probability of a node of degree k is k to power minus r, where r is a number between 2 and 3. Social scale-free networks describe well the social dynamics, and this is something that we will use to model in our model. Prior study of modeling heroin addiction or opioid addiction and spread shows that classical epidemic models can be used for modeling drug addiction. Modeling the HIV and opioid epidemics leads to a co-infection type of model. Co-infection models for 2 strains or 2 diseases have been investigated for many disease combinations. And modeling opioid dynamics in a population is relatively new. It has been around in the last 5 or so years. And we study here for the first time a co-infection of opioid use and HIV in a network setting. So in what follows, I will introduce the opioid HIV model. First, I will introduce the between host model without a network on it. And then I will introduce the network that is imposed on the between host model. And finally, I will introduce the within host model, which is linked to the between host model for multiscale model, for obtaining a multiscale model. So here is a flow chart of the between host model of opioid and HIV. So S is the class of susceptible individuals. T is chronological time. U is the class of opioid addicted individuals. V is the class of HIV infected individuals. Small I, which is structured by chronological time T and time since infection tau, is the density of co-affected individuals. That means individuals who have both HIV and are opioid users. And A is the class of AIDS individuals. So the way the dynamics goes is that susceptible individuals can become infected with HIV. The force of infection in this case is called lambda V. And opioid addicted individuals can get addicted with force of infection lambda U. You know that HIV is a non-treatable disease, so there is no treatment here, but opioid addiction can be treated, and individuals are treated at the rate delta U and can return to the susceptible class. Opioid addicted individuals can get into a contact with an HIV infected individuals at force of infection lambda V, which is magnified by a coefficient called QV, and become co-infected with HIV and opioid addiction. The same is true for the HIV infected individuals. They can get into contact with opioid addicted individual and become opioid addicted with the force of infection lambda U with the coefficient of enhancement QU, and also become co-affected by both diseases. Again, co-affected individuals can be treated at the rate delta and become infected only with HIV, but drop the addiction to opioids. And individuals infected with HIV, which are individuals in class V and individuals in class I, can both progress to the AIDS class. From the class V, they progress at the rate gamma V, and from the class I, they progress at the rate gamma I, which depends on the time since infection tau. Natural death rate is mu. That happens for, out of all classes, so people die from natural causes. And DU is the death rate from opioid addiction. DV is the death rate from HIV infection. DI is the death rate from co-affection. And DA is the death rate from AIDS. Recruitment is at, happens at lambda S. So the model as described by the flow chart takes this form. It's a relatively complex model. So the rate of change of susceptible individuals happens through recruitment, which happens at a constant rate called lambda S. And susceptible individuals move to the opioid affected class at the force of infection lambda U, and they move here. And move to the HIV infected class at the force of infection lambda V, they move to the class V. They die from natural causes, or opioid affected individuals may recover at the rate delta. So opioid affected individuals are recruited at force from susceptible individuals at the force of infection lambda U. They can get into contact with HIV infected individual with the force of infection lambda V and enhancement factor QV, and move to the co-affected class I. And they can die from natural causes, from disease-induced mortality, or they can be treated and become susceptible. HIV-infected individuals come from the susceptible class upon infection with HIV at the force of infection lambda V. They can get into contact with opioid-affected individual and become opioid-affected at some enhancement factor QU. So they move to the co-affected class. They die from natural causes mu, die from the disease-induced mortality DV, or move to the AIDS class at a rate gamma V. Infected, co-affected individuals, the rate of change is given by this first-order partial differential equation. And this happens, the rate of change decreases at the natural death rate mu, the disease-induced death rate DI, the progression rate to AIDS gamma I, and those individuals who are treated for opioid addiction at the rate delta sigma tau move to the HIV-infected only class. The newly co-affected individuals go into the time since infection being 0, into the class which has time since infection equal to 0. And AIDS individuals are recruited from those who progress to AIDS from HIV infected status only, or those who progress from AIDS from co-affected status, and they die from natural causes or from AIDS. The force of infection, of HIV infection, has the following form. So lambda V obviously has to depend on all classes that are infected by HIV. So this is the class V with the coefficient beta V1, and the co-affected class I of T and tau with tau dependent coefficient beta V2. And here we are summing all over all individuals which have different times since co-affection tau. N is the total population size, and in the total population size we do not count the AIDS individuals. So this is the sum of S plus U plus V plus the integral of I. The force of opioid addiction, lambda U, has a similar formulation. So it has a coefficient beta U, and the sum of all classes that are opioid affected individuals, that is U of T, and the integral of I in terms of tau, also divided by N of T. The model is linked to a within host model, which we will introduce a little bit later with the network model. So now the way we have this between host model, we will introduce a scale-free network on this model. So the network has a number of nodes. Each node has a degree k, and k varies from 1 to n. So small n is the maximal degree of a node in the network. We write the known network model for the network by combining all S, U, V, and I, and A individuals of the same degree. So we have a differential equation for susceptible individuals of degree K, so SK, a differential equation for opioid addicted individuals of degree K, so a differential equation for UK, a differential equation for HIV infected individuals of degree K, so that will be VK, and a partial differential equation for co-affected individuals of degree K, so IK, as well as AK. A common notation in network models is this bracket K notation, which is a sum of K, PK, where PK is the probability of a node of degree k. Obviously, since we are summing here by k, this does not depend on k, it's just a constant, but it's a traditional way to denote that this is called average degree in the network, this bracket k. The forces of infection of the network model take the form. For each node, we have a force of infection of HIV denoted by lambda Vk, and we average them over the network with kpk lambda Vk for k1 to n, divided by the average degree of the network, or bracket k, where the force of infection of nodes of degree k is beta V1 k Vk plus the integral of beta V2k Ik over nk, where nk is the total population size of degree k. So this is the sum of sk plus uk plus vk plus the integral of ik. Sk are susceptible individuals of degree k, uk opioid users of degree k, vk is HIV infected individuals of degree k, and ik are the co-affected individuals of degree k with time since infection tau. The force of infection of opioid addiction is defined as lambda u, which is the sum of lambda uk. And lambda uk is defined the same way as in the known network model, but with index k. So this is beta u uk integral of ik over nk. So we recast the known network model into a network model. So the rate of change, this is pretty similar as before. The rate of change of S, K, so K is the degree of the node, of a susceptible node, is the recruitment of susceptible nodes of degree K minus the force of addiction with the opioid addiction of a degree K S node, minus K, the force of infection with HIV of a degree K susceptible node, minus mu, that's the natural mortality or disintegration of the degree K susceptible nodes, plus the recovered degree K nodes infected with, affected with opioids. The rate of change of opioid affected nodes or individuals increases with those susceptible of degree K individuals who become opioid addicted, decreases by those opioid addicted individuals who become HIV infected, and those move to the co-affected class, and decreases by those who die from natural causes, disease-induced mortality, or become treated for opioid addiction and become fully susceptible again. HIV infected individuals of degree K increased by those who become susceptible nodes or individuals of degree K who become HIV infected, and decreases by those who HIV infected individuals who become opioid addicted as well, and those individuals move to the co-affected class. Decreases by those who die from natural causes, from disease-induced mortality, and those HIV infected of degree K who move to the AIDS class of degree K. Co-affected individuals of degree K, the rate of change, which is a partial differential equation, is given by, they decrease by those who die from natural causes, from disease-induced mortality, from the joint affection, progress to AIDS, or become treated at some reduced success rate sigma tau, but that they're nonetheless treated from opioid addiction, and they move to the HIV infected class. So this is pretty much what was the no network model. There is this coefficient Ks. The reason why we have the coefficient Ks is because data, as we will see later, data for within host HIV dynamics, so CD4 cells, viral load, and others of the sort are typically given in days, while data on between host level, which are HIV deaths in the population or HIV new cases or opioid deaths, all of that are given in years. So for us, time tau is measured in days, while time t is measured in years. So Ks is the conversion coefficient between tau and t. As I said, this is a multiscale model. So this is the between host model. In the model is nested multiscale model. So we have to augment it with an HIV, it will be a modified HIV model. The modification includes the opioid drug concentration, C of tau, and its impact on the average susceptibility of target cells. So if you're familiar with within host HIV models, the first three equations are just a traditional target cell limited HIV model. T is the target cells, the rate of change, and this is from time with respect to time since infection. So T is a function of tau. And these are recruited at the rate S. They are disintegrated at the rate dt, and they get infected by the virus VI at the rate K, which depends, however, on the opioid drug concentration Kc. So those cells, target cells, which become infected, they move to the infected target cell class. So Ti are the infected target cells, whose rate of change increases with the newly infected target cells and decreases at some disintegration or cell death rate, delta I. Infected target cells produce viral particles, so the rate of change of the virus, VI. The infected target cells produce viral particles at some rate pi, and the virus is cleared from the body at some rate small c. And the drug concentration is modeled by a simplified logistic model, namely recruitment or infusion rate lambda minus disintegration rate dc and c. The function kc is taken to be a coefficient called beta 1 times c over c plus another constant c0, which is the half saturation rate. The functions, so the within host model and the between host model are linked through the expressions for di of tau, gamma I of tau, and sigma of tau as a function of the within host variables. And these expressions are specific, as well as the transmission rates beta V2K of tau. Beta V2K of tau is taken as some constant beta V2K times the within host viral load as a function of tau over a half saturation constant BK plus the viral load. This is a typical saturation form of beta K, since it is not expected that this will grow as fast as the virus grows. Gamma I is modeled as gamma 0 times the viral load I. DI, this is the death rate of co-affected individuals, is a constant, the target cells at 0 minus the target cells at tau, plus some additional constant D1. And the coefficient of reduction or enhancement of treatment of co-affected individuals, sigma of tau, is modeled by a constant sigma 0. So the complete model consists of the within host model, the between host model, and the linking functions which connect the two models. So we have been able to derive some theoretical results for the network opioid HIV model. I will summarize them here. We have been able to compute explicit forms of the basic reproduction numbers, RU of opioid use and RV of HIV infection. So RU has this form. RU is N times beta U over DU plus mu plus delta. If you remember, N was the maximal degree in the network, and beta U is the opioid addiction transmission coefficient. DU is the disease-induced death rate of opioids. Mu is the natural mortality, and delta is the treatment rate. RV is the reproduction number of HIV. This has a more complicated form, which sort of comes from the force of infection. If you remember, it had a similar form. So K is the degree in the network. Here it's just a dummy variable with which we sum. So we have K squared, PK, and then beta V1 K over mu plus dV plus gamma V. And that is divided by the average degree in the network, bracket K. So remember, bracket K is just a number. It does not depend on K. So our system has a disease-free equilibrium, which is hardly surprising if you work with epidemic models, called E0. The disease-free equilibrium has a non-zero value for the S components and zero values for the U components, V components, and co-affection components I. The A class has been dropped from the system, so we are not investigating it here. So the results do not include the S class. SK0 for any K is lambda K over mu. Besides the disease-free equilibrium, we have found two semi-trivial equilibria, one corresponding to opioid transmission and another corresponding to HIV transmission. So we call E1 star the semi-trivial equilibrium corresponding to opioid transmission. So this has non-zero values in susceptible and opioid addicted individuals, but zeros for V and small I. And HIV here does not exist in this equilibrium. The equilibrium E2 is the one corresponding to HIV transmission. So opioids do not exist in this equilibrium. This has non-zero entries for S and V, but 0 entries for U and for small I, co-affected individuals. So this is, we can compute quite a bit of S and U, the explicit expression on these entries, but I didn't include them because they're not they're kind of complicated. And here, the first subscript counts the nodes. So S1 is susceptible individuals of degree 1. And the second subscript counts this subscript, the number of the equilibrium. So we have S1 through SN1. And the second here, again, the first node counts the degree in the network, and the second node counts the number of the equilibrium. So we were able to establish that the co-infection model always has a unique disease-free equilibrium, E0 star. Besides that, it has a unique boundary equilibrium E1 star of opioid spread if the basic reproduction number RU is greater than 1. and a unique boundary equilibrium E2 star of HIV transmission if the basic reproduction number RV is greater than 1. We have also been able to establish that, yes, I see a question. Do you wish to ask the question now?
I think, madam, we can take up at the end.
Okay. The unique disease-free equilibrium E0 is locally stable if the maximum between the two reproduction numbers, RU and RV, is smaller than 1. The unique disease-free equilibrium is unstable if the maximum between RU and RV is bigger than 1, which means at least one of the two is bigger than 1. We have further been able to establish that the unique boundary equilibrium E1 star is locally stable if the invasion number of HIV, which is called RVI1, that one is just a notation, it doesn't mean anything, is smaller than 1, and it is unstable if the invasion number of HIV RV1 is greater than 1. The unique boundary equilibrium E2 is locally stable if RU1, that is the 2, RUI2, that is the invasion number of opioid addiction. Again, that 2 is not a square, it is just a notation. And U denotes the opioid addiction, and I says that this is the invasion number. Is smaller than 1, and it is unstable if the invasion number of opioid addiction, RUI2, is greater than 1. These are a few theorems or remarks which we have not been able to prove, but not at least in the network model, but we surmise they may be true. So assume that RU is greater than 1 and RV is greater than 1. There exists a coexistence equilibrium E star of the opioid HIV co-infection system if both invasion numbers of opioid addiction and HIV, RUI2 is greater than 1 and RVI1 is greater than 1. So this we have been able to observe in simulations, but we have not been able to prove that theorem. We just surmise it is true. The following statement may also be true. It will be a theorem if we could prove it, but we haven't. So it is assumed that RU is greater than 1 and RV is greater than 1. There exists a coexistence equilibrium E star of the opioid HIV co-infection system if both invasion numbers RUI2 is less than 1 and RVI1 is less than 1. The difference in these two scenarios, here the invasion numbers are greater than 1 and here the invasion numbers are smaller than 1. The difference is that in both cases, a coexistence equilibrium exists. But in the first case, in the theorem case, E star is typically stable. So when you simulate, you can catch it, right? The solutions approach an equilibrium, coexistence equilibrium. So you can observe that in simulations. But in the second scenario, E star is usually unstable. So you cannot observe it even in simulations. So now I want to talk about parameterizing these models. So since we always want to do some simulations, and to do simulations, we need parameter values. And parameterizing this model from the literature is difficult. So we use fitting to data to parameterize the model. So we were not able to find HIV social network data, although we are sure such exists. For instance, that network that I put at the beginning is, it's a picture of a network, but it is made, the picture is made based on actual data, so the data exists. However, we were not able to obtain them. And also the network data will be static, meaning that they're kind of snapshot in time, not dynamic. So So I don't know how helpful that will be even if we had them. Thus, we parameterized a single node or no-network version of the model, or this original version that I introduced. For the within-host model, we had data on viral load and CD4 cells in monkeys treated with an opioid. And for the between-host model, we had various data sets for the population level HIV. These data sets are all from the United States. We use data on HIV diagnosis, HIV death, and opioids deaths. So we fit a total of 5 data sets. So these are the within-host data sets of viral load and CD4 cells, and the between-host data sets of HIV diagnosis, HIV death, and opioid deaths. So fitting this multiscale model can be done in 2 ways. The first way is sequentially. So what this means is that the within-host model is not is linked to the between-host model, but it can be the between-host model does not participate in a sense into the within-host model. So it is somewhat separated from the between-host model, and it can be fit separately by itself to the within-host data. Then it can be fixed. So we take the within-host model, we fit it to the within-host data, and we fix that. And then we take the between-host data, and we fit the between-host model while holding the within-host model fixed to what we fitted it originally by itself. This is called sequential fitting. It can also be fitted simultaneously when both the within-host and the between-host model are fitted simultaneously to all 5 data sets. So we prefer to fit simultaneously the within-host and the between-host models, as our prior research has shown that this type of fitting leads to more or better identifiable parameters. However, typically what happens is that we first fit sequentially so that we can identify some parameters which will place the curves near the data. And then we fit simultaneously so that we can improve on those parameters. After this procedure, we have obtained the following fits, and this is the first figure, gives the CD4 cells. The blue line is the solution of the that comes from the model, and the red dots, I hope you can see them, are the data points. Although the fit does not look great, keep in mind that we are fitting a lot of equations to a lot of data sets. So even placing the curve near the data is useful and difficult and useful. The second figure is the viral load. Here, the fit of the model, which is the blue line, is a lot better to the data. You can see most of the data are on or near the blue curve. The between-host part of the model, we were fitting to AIDS diagnosis in the United States in the years 2000 to 2018. The data are given by these gray bars. The time is in years. And the simulations with the model is this, let's call it red curve. And you can see that the red curve actually follows the data pretty accurately for the most part. Number of deaths due to HIV in the United States, again, years 2008 to 2018. Here, the red curve for the simulation for the model is not as good of a match to the data, which are the gray bars, but at least it is in the general neighborhood of the data. And finally is the number of deaths due to opioid overdose. in the United States, years from the year 1999 to 2018. And again, the gray bars are the data points and the red curve is the solution from the model. And you can see that it pretty accurately respects the data. So it's a pretty reasonable fit. So we are fitting the 4 equations of the within host model together with the 6 equations of the between host model, or 5 equations of the between host model to the 5 data sets. So, so when we fit, we obtain parameter values. The question is this the only set of parameter values that will give us this good of a fit, or this same fit, or are there others? So this question is called the question of identifiability. So given data, are we capable of estimating the parameters of the model? So you can think about this way. I often describe it as the following problem. Suppose you have a single point and you want to fit a line through it. So obviously there are lots and lots of lines which will fit perfectly through this single point, but you still don't know, you have one parameter of the line, namely the slope of the line, which you do not know how to estimate from a single point. So this is an identifiability question. If you do that with software, I mean, it will give you a value for the slope, but how good is it? So this is an important question. Can we or can we not identify the parameters of our model from the data that we are given? So there are 2 types of identifiability that we consider, structural and practical identifiability. Structural identifiability studies whether the parameters can be uniquely identified from noise-free and ideal data, meaning data are very frequent and they come from all parts of the solution curve and all of that. So whatever you want to know or have about the data, you have it. So typically the structural identifiability is a problem that studies whether the model itself is structured in a way that, given this and that data sets, that model can be used to identify its parameters from the given data sets. Practical identifiability is what the name says, whether we can or cannot, or with what accuracy we can determine the parameters in practice. That means our data are not noise-free and our computational software is not error-free, and the data might be clustered in some parts of the curve and not in others, and are not given with many points, but are spaced at large spacings, and all those difficulties that one normally has with actual real data. So we studied the structural and practical identifiability of the within host model. The full model is too complicated to do much with it. So we studied the structural identifiability of the ODE model, the within host model, using software called DAISY. So DAISY can be asked whether ODE model, so you give the ODE model and then ask DAISY to determine the structural identifiability. And for this specific model that we have, DAISY stated that the within host model is not structurally identifiable with respect to the data we had, which were the viral load and the CD4 cells. So if a model is not structurally identifiable, there are a couple of approaches that can be used to improve the identifiability. One of them is to rescale the model, and we do not use that here, although we have used it in the past. And the second one is to determine some parameters which will lead to identifiable model. And if we go back to our example with the single point and the line we want to take through the single point. So suppose you know from an outside information what the slope of the line is. If you know the slope, then you can determine the intersection point, because then the line only has two parameters and you have one data point. So that problem will be, the parameters of that problem will be completely identifiable, even though the original problem, take a line through a single point, is not identifiable, since there are lots of lines doing that. So determine some of the parameters from external information which will lead to an identifiable model. This is a very common procedure that we use, and we have used it here. So if you recall, K of C was the infection rate of the target cells by the virus, and it depends on the concentration of the opioid, which is C, through this formula. So structural identifiability analysis reveals that all parameters are identifiable except C, DC, lambda, and C0. We fix C and DC. C is the clearance rate of the virus, and this has been estimated in many papers before, HIV papers before, so it's not hard to estimate from the literature. And DC is the half-life of the opioid, which is known. The opioid was known in the paper that we took the data from. And lambda, which is the drug infusion rate, was also known. The paper was giving how often were the monkeys given the opioid. So DAISY, on the other hand, has the strength of giving which parameter combination. If some parameters are not identifiable, DAISY gives parameter combinations that are identifiable, and it stated that lambda over C0 is identifiable. So once we choose a value for lambda, based on what we know from the paper that the infusion was done of the opioid, then we will also know C0. So that makes the model identifiable just by fixing 3 parameter values in the model. We also study the practical identifiability, and we do that with Monte Carlo simulations. Monte Carlo simulations are a computational tool to figure out how good of a fit one can obtain given certain data, which are not necessarily perfect. The way Monte Carlo simulations work is one fits the model to the data and obtains something called true parameters, in quotations, since we don't know whether they are true parameters, but we call them true parameters. And then we simulate the model with the true parameters, and we pick data from the same time at the same time points from the simulation of the model, and then we add then we make m new data sets by adding 5% noise to this data. So to this picked data from the curves of the model, we add 5% noise randomly and make m new data sets. Then we add 10% noise and we make m new data sets. And then we add 20% noise and make another m data sets, and 30% noise and make another m data sets. So then for all those data sets, so we have 4 times m data sets, we feed the model to this data, and we estimate for each noise level, we estimate m parameter values for each parameter. And then we use the true value, p hat k is the true value of the parameter, which we obtained from the original fitting. We subtract the estimated value of the parameter from the m data sets, and we divide by the true value of the parameter. And we add for I between 1 and m for the m data sets, and we multiply by 100. So this is a percentage. So these are called average relative error. You can see that this is a relative error, and they're added for all m data sets. The average relative errors of the estimated parameters are given in the table. So here is the table. This is the noise level. These are the values of S for the noise level 5%, 10%, 20%, 30%. So the average relative error for S at 5% noise in the data is 3.7%. The average relative error with 10% noise in the data is 7.2%. So obviously the errors with which we estimate, or the deviation with which we estimate S with this sort of error in the data is not as large as even the error in the data or the noise in the data. So this is, we consider this good, or we consider that this actually this parameter is possible to estimate. But these are the average relative errors with which it can be estimated given the noise in the data. Now, in practice, we have observed that real data, epidemiological and immunological real data, usually have 20 to 30% noise. So we're looking at the errors in estimating ACE between 15 and 26%. And DT can also be estimated with a reasonable error. So we are looking at, for realistic noise levels, at 11 to 20% error in estimation of DT. On the other hand, B1 has at 30% noise has estimation error of 7.10 to the 9%. So obviously we cannot estimate B1 anywhere close to what would be convincing. Delta I is also reasonable and possible to estimate. Pi is also reasonable and possible to estimate. C0, however, is the error at 30% noise in the data is 6 times 10 to the 9. So again, we cannot estimate C0. So from this table, we conclude that with C, DC, and lambda prefixed, we have fixed those to make the model structurally identifiable. Even though the model is structurally identifiable, there are two parameters that are not practically identifiable, namely beta 1 and C0. They're not identifiable in this case. So the only thing one can do is fix one of them and repeat the Monte Carlo simulations, which is what we do. We chose C0 to be, it's a half saturation constant. So we estimated it to be 6530. So we fixed it at this level. And then when we run the Monte Carlo simulations, I did not include the table, but the identifiability improves dramatically, and all parameters become, all remaining parameters become identifiable. So we, of course, would like to know what kind of control measures we should take or do to improve the situation of HIV transmission in opioid addiction. So to do that, we computed elasticity results. The elasticity of a quantity Q, just any quantity called Q, with respect to the parameter P, is defined as follows. So the elasticity is called epsilon, and that is the partial derivative of Q with respect to the parameter P. We, of course, assume that Q depends on P, multiplied by the quotient of P over Q. So what is the meaning of the elasticity? The elasticity epsilon of the quantity Q with respect to the parameter P says that 1% change in the parameter P will lead to epsilon% change in the quantity Q. Elasticity is positive if Q is increasing with the increase in P, and negative if Q is decreasing when P increases. So with this baseline information, we computed the elasticities of the invasion reproduction number of the invasion numbers with respect to the basic reproduction numbers. So A is the elasticity of the invasion number of opioid, RUI2, with respect to the opioid reproduction number, RU. B is the elasticity of the invasion number RUI2 with respect to the reproduction number RV, that's the reproduction number of HIV. C is the elasticity of the invasion number of HIV RVI1 with respect to the reproduction number of the opioid RU. And D is the elasticity of the invasion number of HIV RVI1 with respect to the reproduction number of HIV RV. So A, B, C, and D are plotted in this bar chart. A is almost 1, B is a small number and positive, C is a large negative number, and D is also almost 1. So we see that the largest effect in the invasion numbers is in C, that means in the invasion number of HIV with respect to the opioid epidemic. So the elasticity of RV with respect to RU being large and negative says that increasing the opioid reproduction number with 1% decreases the invasion capabilities of HIV with approximately 2.5%. The negative sign suggests that the opioid and HIV epidemics are in competition. So you weaken one of them and you strengthen the other. And this leads us to believe that decreasing the opioid epidemic is a promising strategy. Parameters not involved in the invasion numbers, but potentially important for control are QU and QV. So we compute the elasticities of the invasion numbers with respect to QU and QV. W is the elasticity of the HIV invasion number with respect to QU. Remember, QU and QV are the coefficients of enhancement of co-affection with opioid or HIV. QU is with opioid and QV is with HIV. X is the elasticity of the invasion number of HIV RVI1 with respect to QV. Y is the elasticity of the invasion number of opioid RUI2. This is not a square, it's just a notation with respect to QU. And Z is the elasticity of the invasion number of opioid with respect to QV. In here, the values of W, X, Y, and Z are plotted. It's not a bar chart because Z has a very large and negative value. If you plot this as a bar chart, the others will not be visible because they are relatively small numbers in absolute value. So Z is the largest, it has the largest value and it's negative, which says that the invasion number of the opioid epidemic with respect to QV is very, has very substantial, the opioid epidemic, the invasion capabilities of the opioid epidemic depend very substantially on QV. Also, that means that the invasion capabilities of the opioid epidemic are increasing when QV is decreasing, since the elasticity is large and negative. And this suggests that the key to controlling these two epidemics is to decrease the HIV infection in drug users, or that is the coefficient QV, the parameter QV, and to combat, so this will increase the invasion capabilities of the opioid epidemic. So in order to stop that, we have to combat the opioid epidemic at the same time. So these are the control measures that seem to have the maximum impact based on this kind of analysis. And finally, I will summarize the results. So we formulated a no-network multi-scale model of HIV and opioid addiction. We formulated a scale-free network version of the above model. For the no-network model, we fitted the model to 2 within-host data sets and 3 between-host data sets. So total of 5 data sets. We studied the structural and practical identifiability of the within-host model. We find that the within-host model can be both structurally and practically identifiable if several, actually 4 parameters were fixed. We analyzed the network model. We found that it can have a disease-free equilibrium and 1 equilibrium corresponding to each disease. Simulations suggest that the co-affected equilibrium exists, which is possibly stable, at least locally. We also showed that the stability of the boundary equilibrium depends on the reproduction numbers and invasion numbers. We computed the elasticities of the invasion numbers with respect to the 2 reproduction numbers, as well as with respect to QU and QV. We find that the most influential elasticities are the elasticity of the invasion number of HIV with respect to the opioid reproduction number, showing that the 2 epidemics are competing, and the elasticity of the opioid invasion number with respect to QV. Based particularly on this second, the importance of this second elasticity, we summarize that a very efficient control strategy is to reduce QV, that is the coefficient with which opioid-addicted individuals become HIV infected, and to combat the opioid epidemic. With this, I want to acknowledge NSF support, but all views that we express in this talk are those of the authors and not of NSF. And the authors of the papers on which this talk is based, it's based on 2 articles. Both are joint with Nej Betunger and Churnik Gupta. And one of the articles is actually published, the other one is still in progress, but nearing submission. Thank you for your attention and patience. And now I can take questions.
Yes, thank you so much, madam, for nice presentation. Let us see some questions. One, I can see that asking force of infection, meaning of the term force of infection.
The force of infection is the strength with which a susceptible individual or other type of individual becomes infected with a disease. It is usually measured by the number of infected individuals over the total population size, or just the number of infected individuals.
Madam, the simulation part, what tools you use for the simulations of immunology?
So we use MATLAB, and the code is all proprietary. Nej Betunger is the primary person who writes the code. She has a website on GitHub where you can obtain the code if you want to.
Okay.
So she places the code. I don't know the latest code, whether she has put it up, but she places the code on her GitHub website and you can get it from there.
I think there is another. What is the advantage of network model?
Incorporating, so networks are a way to model not homogeneous contact structure. So you know that disease transmission depends very seriously on the contact, right? On the contact structure and the contacts and how many contacts and who makes contacts with whom and whether the contact is good enough for transmission of the disease. But with ordinary differential equations, we assume that all contacts are the same, right? They have certain duration of time, and I mean, per number of contacts, they're measured by number of contacts per unit of time. And all individuals in the population, or most individuals in the population, have the same contact structure. When a network structure is introduced, then the contact structure depends on the network, right? So the network says this individual has K contacts with that individual, but this other individual has K plus P contact with that other individual. So the contacts, the number of contacts in the network are explicitly incorporated. So the diversity of the contact structure is better modeled with a network model.
Ma'am, about data sets, data that you talk about is, what is the source? Is it available? I mean,
so yes, so the within host data came from an article, and that will be cited in, let me see. So the article that fits the no-network model to the data is already published. It is published in Mathematical Biosciences and Engineering. And this is an open access journal, so you can read it freely on the web. And that article will cite the article from which the data comes, which is another published article. That is the within host data. The between host data come from the CDC website. CDC has a website where it publishes data. I'm sure India does so too. So this data come from the CDC website, the between host data.
I think there is no more query, Sam.